Alright, next we're going to be looking at excitation-contraction coupling. This is going to be step 2 in skeletal muscle contraction. And it's initiated by that impulse or electrical current that we call an action potential arriving to the sarcolemma. That action potential is then going to propagate or travel along the entire sarcolemma into the T-tubules that are connected to the sarcolemma. That's going to lead to the release of calcium from the sarcoplasmic reticulum because the T-tubules can communicate to the sarcoplasmic reticulum at the terminal cisternae, or the parts that make up the triad. The release of calcium is the final go signal for contraction, so that's going to initiate the contraction cycle, which includes attachment, pivot, detachment, and return. Now with step 2, I do recommend watching the video called A&P Flicks, Excitation Contraction Coupling. It's going to show you how the local depolarization that we consider the action potential arriving at the junctional folds is going to be just enough to propagate or allow for travel of that electrical impulse towards the T-tubule. And once that electrical impulse travels into the T-tubule, it's actually going to activate a calcium release channel that connects the T-tubule to the sarcoplasmic reticulum. That will release calcium into the sarcoplasm, and that will allow calcium to then bind to troponin and move the troponin-tropomyosin complex out of the way, and that way we can move on to step 3, where myosin and actin come together to form a cross bridge, and we see the contraction cycle. So excitation-contraction coupling is very short, because all we're going to do is see the propagation of the action potential, go down the T-tubule, and lead to calcium release. That's excitation-contraction coupling. We couple that excitation, the action potential, to the coupling of myosin and actin, which can happen because of calcium release. So that brings us to step 3. And we've already kind of looked at step 3 when we looked at the sliding filament model of contraction. So let's review it. In the sliding filament model of contraction, actin, also known as the thin filaments, will slide past myosin, also known as the thick filaments, and as the myosin heads start pulling on the actin, this creates greater overlap. So it creates greater overlap between actin and myosin. Keep in mind that the actin and myosin myofilaments do not change length. Instead, we see increased overlap from these filaments, and that shortens the sarcomere, but not the filaments. So in a relaxed state, the thin and thick filaments overlap only slightly, but they always overlap. And upon stimulation, we see increased overlap because the myosin head that binds to actin initiates sliding. And each myosin head binds and attaches several times during contraction to actin. It actually acts like a ratchet or a propulsion force to generate tension to propel the actin toward the center of the sarcomere. And this keeps occurring, and throughout this event, this sliding filament model of contraction, the sarcomeres in each myofibril shorten. And this builds tension. So let's take a closer look at the contraction cycle. Let's start with the binding of myosin to actin, which occurs at the end of excitation-contraction coupling. That's possible because of ATP that was bound to myosin being broken down, and calcium that was released from the endoplasmic reticulum, or the sarcoplasmic reticulum of a muscle cell, entering the sarcoplasm. Once myosin binds to actin, it releases its inorganic phosphate and binds even stronger to actin. And that also initiates a power stroke or a propulsion force where actin gets pulled toward the middle of the sarcomere. Then the myosin head releases the broken down ATP, specifically in the form of ADP or adenosine diphosphate. That leaves myosin in a really low energy form. And that's then going to lead to its detachment when a new ATP molecule binds to the myosin head. When the new ATP molecule binds to the myosin head, that leads to the unbinding of myosin from actin. But it can be reset, and the cocking of the myosin head is when it moves backward into its starting position, and it's in a really high energy form, having just broken down the new ATP into ADP, or adenosine diphosphate, and an inorganic phosphate. And that moves us back to step 1. where myosin is then going to bind to actin, then release inorganic phosphate, bind stronger, do the power stroke, then detach once it binds new ATP, and then keep going. It is the hydrolyzation of ATP that resets the myosin head, but this repeats over and over again as long as calcium and ATP are present and available. So if you would like to look at these events sequentially as opposed to a cycle, you could look at them this way. With step 1 being cross-bridge formation, when the myosin cross-bridge attaches to the actin filament, with step 2 being the working or power stroke, where the myosin head pivots and pulls actin filament towards the middle of the sarcolemma, or the middle of the sarcomere, called the M line. Cross-bridge detachment, where ATP attaches to the myosin head, and the cross-bridge detaches, being step 3, and step 4, the cocking or resetting of the myosin head, where energy from the hydrolysis or breakdown of ATP resets the myosin head into the high energy state. I also recommend watching the cross-bridge cycle video called AMP Flicks Part 3, the cross-bridge cycle. But you do want to make sure you come back and review all 3 steps of skeletal muscle contraction, including step 1, the neuromuscular junction, step 2, excitation contraction coupling, and step 3, cross-bridge cycling. There is an animation listed in your online PowerPoint, so you can go through and review those 3 steps. Next, we're going to be looking at what's actually happening in the sarcomere during the cross-bridge cycling, so during that sliding filament model of contraction. We know we're going to see shortening, but what does it look like?